Hello everyone, welcome back to our channel. And in today's video, we are going to continue with our digital electronics series, which we are studying for the UPSC Engineering Services examination. Right, so this is a free initiative that I want to tell you all very first, wherein we are going to provide lectures and notes. We will provide lectures onto our YouTube channel, and all the notes will be provided on the Telegram channel. So the link to the both is on to the WhatsApp. Sorry, in the description it is being given. So make sure you join the Telegram group and as well as subscribe to our channel so that you will be notified whenever we are live and you can easily attend the live sessions. Right, so now let's get into and continue with our digital electronics. So yesterday we have already seen what Boolean representation is. Then we have seen the K-map reduction techniques for Boolean expression. Now we would dive into and we will first understand what combinational logic circuits are, and then we will see the different combinational circuits. Starting with today, we will start our session with what basically a full adder is. Right, so let's see. So basically a full adder is nothing but a combinational logic circuit which has three inputs and two outputs. Now obviously it's an adder, right? So whenever you add two numbers, so you would have the first number to be A, you would have the second number as B, and if there is a carry that has been generated, you need to add it. So you have one more input, that is C in, nothing but carry input. So you can see over here, these are the three inputs and we have two outputs. The two outputs are nothing but the sum and the carry. Okay, now let's look at the full adder truth table. This is the full adder truth table wherein we have three inputs, so we will have 8 logic combinations, and this is the corresponding sum and carry outputs. Right? Okay. Now first, this is the truth table. You can pause the video and note it down in your notebook. And this is the block diagram of a full adder. This also you should know. Now next, let's look at the equations for the output equations for sum and the carry output, right? Okay. So now you can see this is the truth table, and from this same truth table we have drawn the K map. So we have three inputs over here, input A, B, C, right? A would have two combinations 0 and 1, and BC will have four combinations 0, 0, 0, 1, 1, 0 and 1, 1, right? So from this K map you can see this is the K map, and there are no ones pairs that are forming. So we will consider ones as the individual and we will write the equivalent term, right? So in here, this is the first one. So this one would be represented as A, B bar, C. Then the second one is A bar, B bar, C. The third term will be A, B, C. The fourth term will be A bar, B, C bar, right? Now, this is what you add. So, sum would be the addition of all the sums because it is sum of products, right? Okay. Now, next we would simplify this using simple Boolean algebraic laws, and this is the output that we get. So, the sum of a half adder is equal to C XOR A XOR B, right? So this is an important equation that you need to remember directly. Next, moving on to the carry output, same, we have drawn a K-map, and using the K-map we have simplified it, and this is the equation of the carry output. I am marking a star. Make sure you pause the video and write this in your notebook, right? Now let's look at the logic diagram. So you can see this is the simple logic diagram. We have drawn this logic diagram based on the carry equation and the sum equation. So the sum is nothing but A XOR B XOR C, right? So in here we will be using a 3 input XOR gate, right? Then we have the next carry equation, which is AB plus BC plus AC. That means we would require three AND gates, and then we would OR them together using a 3-input OR gate. So this is a logic diagram of our full adder, right? Now let's move on to the next combinational circuit, that is nothing but our half subtractor, right? Okay. So a half subtractor has two inputs and two outputs. What are the two outputs? The two outputs would be difference and borrow, right? In case of addition we carry, in case of subtraction we borrow. This is the basic. uh, Yes, so this is the truth table. Since we have two inputs A and B, and we will have two outputs D, that is difference and borrow, right? You can see two inputs, four combinations, and this is the output. Now from this truth table, let's draw a K-map. You can see over here for the difference equation, this is the K-map. And based on this K-map, this is nothing but AB bar, and this is nothing but A bar B, right? This is nothing but equivalent to A XOR B. So the output equation for difference is nothing but A XOR B. Similarly, for the borrow output, we just have 1 0 over here. That means only one term. So that is nothing but A bar B. So these are the two equations that you need to remember. This is the first equation for difference, and this is the second equation for borrow that you need to directly remember, right? Now from this, let's just draw a simple logic diagram. You can see this is an XOR gate that represents the difference of half adder, and this is nothing but the borrow, right? Okay. Next is, okay, now okay, this is the XOR gate directly. Now the whole XOR gate can be also constructed using two AND gates and a OR gate. Okay, so this is the logic diagram using basic gates, and this is the logic diagram in which we have used derived gates. Now let's move on to the next, that is nothing but full subtractor, right? So in full subtractor we will have three inputs. We will have three inputs A, B and borrow in, right? And we will have two outputs, difference output and borrow output, right? So now let's look at the truth table. This is also very similar to the full adder. Full adder also has three inputs and two outputs. Full subtractor will also have three inputs and two outputs, but the only difference could be in the output equations. Right? Now let's look at the draw the K map first from this given truth table. You can see over here from the given truth table, this is the K map that has been drawn. Again here for the difference output, there are no pairs that are forming in the K map. So these are the single individual ones that we keep, and each one would represent a term, right? And then the difference would be nothing but the sum of each terms, right? So this is the equation that is formed. Now when we simplify this equation using the Boolean equations and the Boolean laws, this is the output that we get. It is nothing but C XOR A XOR B, right? This is the difference equation, and this is the borrow equation that we have derived using this K map. So the borrow equation is A bar B plus BC plus A bar C. So this is the equation that you need to remember for borrow, and this is the equation that you need to remember for difference, right? So make sure you write it down in your notebooks. Okay. Now similarly, this is the simple logic diagram of a full adder, right? Okay, very simple. It is rather very similar to the full adder as well. So this is the difference. We are using a single XOR gate, and in here we have three AND gates because of the three product terms, and a single OR gate because we are summing all the individual product terms, right? Now let's move on to the next. Okay, now next is a converter. It's a gray to binary code converter, right? So let's first look at the block diagram. You can see this. This is a simple block diagram of a gray code to binary code. inverter, right? Okay, so it would have, if the gray code is having 4 inputs, it will give us 4 binary outputs. Now let's first look at the truth table. Okay, now you can see this is the truth table. Okay, okay. So what is the binary output, or what we can say is whatever. Okay, one second. Okay, yes, this is the gray. Okay, okay. What you do is you just XOR. Okay, see, these are the gray inputs and these are the gray outputs. Okay, these are the gray inputs and these are the binary outputs. So to obtain that, what you do is you just XOR each term, right? You XOR each term. I will show you the logic diagram first. Okay. So this is the logic diagram that you can see. So each binary term is nothing but equivalent to the XORing of the gray terms, right? So what would B0 be? That means the first binary term would be equivalent to the XORing of each gray term, right? So in this case, this is a gray to binary code converter. So the first binary term would be G0 XOR G1 XOR G2 XOR G3. Similarly, B1 would be G1 XOR G2 XOR G3, right? And B2 will be, that means the third term will be XORing of G3 plus XOR G2, and B3 will be equivalent to the same given binary code. We won't XOR anything. Okay, so this is the simple logic diagram that we have derived from the given truth table over here, right? So this was about the gray to binary code converter. You can okay, one second. The slides have been repeated, I guess. Yes, the size have been repeated. Okay. Now this was about the gray to binary. Now let's look at the n-bit parallel adder, right? Okay. Now the full adder is capable of adding two single-bit binary numbers along with a carry input that we have already seen. So our inputs would be, for a full adder, it is A, B, carry in, and our outputs are sum and carry out. This is in case of a full adder, right? But in practice, we need to add binary numbers which are much longer than 1 bit, right? So to add n-bit binary numbers, we need to use the n-bit parallel adders. That means it uses a number of full adders in cascade, right? Full adders in cascade. So a cascade, as in, if this is the output of the first adder would be given to the input of the next adder. This is nothing but cascading, just like a train. Now the carry output of the previous adder is connected to the carry input of the next adder. This is, I just told you what this is, right? Now let's look at the block diagram. You can see over here. You can see this is the first adder, full adder 0, full adder 1, full adder 2, and full adder n minus 1. So you can see the output of the previous adder has been given as input to the next adder. So this is the simple diagram of n-bit adder. Now let's look at the diagram of a 4-bit, specifically 4-bit n adder. And when I am talking about 4-bit, that means it would have 4 full adders, right? So this is the basic diagram of a 4-bit parallel adder, right? So in here we are having 4 full adders, F0, F1, F2 and F3 respectively, and the previous output is given to the next input, right? Now, yes, now this is a specific IC 7483. One second, I'll show you the diagram first. Yes, this is IC, which is nothing but a 4-bit binary parallel adder. The IC number is 7483. Maybe in some MCQ they might ask you what is the function of IC 7483 or vice versa, right? So this IC has like it's a 4-bit parallel adder, right? So it would add two 4-bit binary numbers. So this is our first binary number. That means it would have four inputs for first binary number, four inputs for second binary numbers, right? And it will give us a sum output in 4 bits. Yes, and then it will have a carry input and a carry output, right? So this is a 4-bit binary adder. So IC, basically IC 7483 will consist of a single 4-bit binary parallel adder. Now what if we cascade it, right? So if we want to add 8-bit binary numbers, then we would cascade two 7483 ICs, right? Because the first IC will act as the first 8-bit number, will give help us give the input to the first 8-bit number, and this will help us to give an input of second 8-bit number, right? And the sum output, if together, will give us a 8-bit output, sum output, right? So this is nothing but cascading of IC 7483. Right, okay. Till then I will display this diagram. You can pause the video and you can draw this diagram. I will just erase the ink on this slide. Okay. Now next, moving on, is a BCD. One second. Okay. But moving on to before moving on to the BCD, let's first look at a 4-bit binary parallel subtractor. Okay. Now, okay. So see, in the binary subtractor, we had used the 7483 IC. To do the subtraction operation, we will be using the 7483 IC itself, but the difference would be that the second binary input has been complemented, right? Because it's a subtraction addition. So say if I have the first binary number as 1001 and the second binary number as 0110, right? So when I subtract it, I'm going to subtract it. That means what is happening is 1001 minus, I need to minus this. That means I need to take the complement of the second binary number. Therefore, you can see over here in this diagram that the B binary number, the inputs, they have been connected with a NOT gate. Okay, so this NOT gate will give us an output over here as 1's complement of B. And then 1's complement of B is being provided to the IC7483, which will give us a difference output, right? So the diagram is very similar, but the only difference is, to act as a subtractor, we need to take the 1's complement of the second binary number, right? Now the same IC 7483 could act as a adder and a subtractor, right? So we would add XOR gates to the second binary input, right? And we would give a common pin called as the mode pin, right? When this mode pin is 0, this IC7483 will act as a adder, right? And when, once again, let me change the color. Yes. And when the mode 0 over here is equals to 1, then it would act as a subtractor, right? Then it would act as a subtractor. Now why is this so? Let me draw the truth table of an XOR gate. So these are the four inputs that we have: 0, 0, 0, 1, 1, 0 and 1, 1. So we all know that sorry, uh, when both the inputs of an XOR are same, it will give a low output, right? When both the inputs are same, it will give an low output, and when both the inputs are different, it will give a high output, right? So you can see over here a comment pin has been connected to this mode. So when mode is 0, which when mode is 0, it would act as a addition operation, and when mode is 1, it will act as a subtraction operation, right? I will erase the ink on the slide. Please take a screenshot of this, or you can draw this in your notebooks. Okay. Now let's move on to see the next combinational logic circuit, that is nothing but a encoder, right? And then we will also see what a decoder is. Let's start with an encoder. So you can see a encoder is a combinational circuit which is designed to perform a inverse operation of a decoder. Okay, an encoder has n number of input lines and m number of output lines, right? An encoder produces m bit binary code corresponding to the digital input number, right? So whatever, it will produce a m bit binary code. That means we are encoding it to a binary code. So the encoder will accept a n input digital word and convert it into a m bit another digital word, right? It will convert it into another digital word itself, but a different one. Now let's look at the block diagram. This is the block diagram of an encoder. As already mentioned, n inputs, m outputs, right? Now let's look at the different types of encoders. The first one is a priority encoder. Then we have something called as decimal to BCD encoder that would convert a decimal number into a equivalent BCD. Then we would have next encoder, which is converting an octal number to a binary coded decimal BCD, and then the last one, which is converting a hexadecimal to a binary coded one. Now let's look at the priority encoder. Now the name says priority. That means it is going to prioritize the different inputs or specific input lines, right? Now, this is a special type of encoder, and priorities are given to the input lines, right? So if two or more input lines are one at the same time, then the input line with highest priority is considered, right? If two inputs having, say, input 1 is 0, and say let's consider input line 2 is 1 and input line 8 is also 1, and say priority has been given in this manner from 1 to 8. That means 1 will have highest priority and 8 will have least priority. That means if in this condition input line 2 and input line 3 are 8 are having same number, same value, that is 1, then the priority will be given to the second input because 8 is having the least priority. I will show you a diagram, it will be simplified. Yeah, so you can see over here, this is a 8:3 encoder. Now what does this 8:3 mean? 8 is nothing but input lines and 3 is nothing but output lines. So it's basically n is to m. N is to m. I guess this color is not visible on the slide. Yeah. So it is n is to m. Right. So this particular priority encoder will have 8 inputs and 3 outputs. Right. Okay. Now you can see over here D0 is having the highest priority and D7 will have the lowest priority. So if we consider D3 is 1 and D6 is 1 at the same time, then the priority will be given to D3 instead of D6. Right? Now let's look at the uh, truth table of a priority encoder truth table of an 8:3. That means it will have 8 inputs and 3 outputs. Right? So now let's see. You can take a screenshot of this, or you can pause the video and draw this in your notebooks. Right? Now next is nothing but a decimal to BCD converter, right? A decimal to BCD converter. Now, uh, okay, so in case of a decimal to BCD encoder, it is nothing but it will have 9 inputs and it will have 4 BCD outputs, because binary coded decimal, right? We consider 4 bits together. So this is how this is the simple block diagram of a decimal to BCD encoder, right? This is the truth table of decimal to BCD encoder. You can pause the video and take a screenshot. Right. Now let's move on to the next, that is nothing but a decoder. So basically a decoder is also a combinational circuit itself, and it will perform the inverse operation of an encoder. Right. Now a decoder will also have n number of input lines and maximum 2 raised to n number of output lines. This can form a simple MCQ question, right? What are the maximum number of output lines formed in a decoder? Then the formula should be written as 2 raised to n. Right now, a decoder is identical to a demultiplexer but without the data input. This could be also asked as a filling the blank in your exam. Right? So this is a simple block diagram of a decoder. And what are the different decoders or types of applications of decoders? They can be used as code converters, BCD to 7 segment decoders, Nilix tube decoders, and relay actuators. Right? Now let's look at the types of decoders. The first one is 2 is to 4, 3 is to 8, and BCD to 7 segment decoder. Right? Now let's look at the first 2 is to 4 line decoder. So that means it would have 2 inputs and it would give us 4 outputs. Right? So this is 2 inputs. Since we have 2 inputs, there are 4 combinations and these are the corresponding outputs. Right? From this given truth table, this is the diagram that we have drawn for 2 is to 4 line decoder. Make sure you draw this in your notebooks because this is something you must remember, right? So a 2 to 4 line decoder will have 2 inputs A and B, right? And then it will have 4 outputs, and the 4 output gates are nothing but AND gates, 3 input AND gates. Now next is a 3 to 8 line decoder, since it has 3 inputs and 8 outputs. Okay. This is the truth table. The truth table will also have 3 inputs A, B and C. So it would have 8 combinations and these are the corresponding outputs. Pause the video and take a screenshot or draw it in your notebooks. Now this is just basic theory that we have already covered. So I'm just giving it a brush up. Right. Now let's look at a comparison between a decoder and an encoder, right? So the input applied is an active input signal, that means the original message signal, right? And a decoder's input is nothing but the coded binary input, right? So this is the original message that is being connected to an encoder, right? The encoder will give us a binary output, and to convert it to its original message we use a decoder, right? So over here we use a decoder, and the input of a decoder is the binary coded input, that is the output of a encoder. And over here again we will have our original message. This is our original message over here, and this is the original message over here. Right, so what is the output generated? It is for an encoder it is coded binary, and for a decoder it is active output signal or the original message. Right, this is something you need to remember, these 2 points, input lines and output lines formula. 2 raised to n input lines, n input lines for decoder. In case of output lines of an encoder it is capital N and it is 2 raised to n. Okay, I'll clear the ink on the slide. Okay, take a screenshot of this, or you can pause the video and write it in your notebooks. Now this is very important over here, I am marking. This is something many people get confused with, right? Okay. Now the operation is simple, but of a decoder it becomes a little complex because we need to convert the original message, right? Now the applications we can see of a encoder, email, video encoders, etc. And a decoder is microprocessor, memory chips, etc. are applications of a decoder. Now let's look at a BCD to 7 segment encoder. seven segment display. So you can see this is the seven segment display that is available. Now each term has been given a specific name. So it starts over here. This one is A, B, C, D, E, F, and G. And over here we have a decimal point, right? Okay. Now let's look at this. Now, whenever we have to form, say for example, we have to code the number 7, right? So to code a number 7, all these following inputs should be 1. That means in our case, to form the number 7, A, B, C, and G should be on, right? Now let me show you a table that it might be easier, easier over here. So you can see over here, this is number 7, and we have already seen for number 7, A, B, C, and G should be on. So you can see over here, A is on, B is on, C is on, and okay, in this case they have not taken the line of 7, but if you take the middle line of 7, then G will also be on. Okay, now pause and tell me what are the different uh, inputs that should be on to form the number 6. Number 6 looks like this. That means what are the inputs that need to be on? A, C, D, E, F, and G. These are the inputs or segments. These are called as segments, okay? A, B, C, D, E, F, G are segments. So these, whenever specific segments have been on, then there is a specific number that has been displayed. Now, we considered the number 6. So in case of number 6, it is A, C, D, E, F, G. So you can see over here, this is number 6. A, C, D, E, F, G are on. So when these are on, the display number will be 6, right? Because this is a 7 segment display, right? Okay. Yes, so this was about the 7 segment display that we have covered over here, and we have seen the different types of encoders and decoders in today's lecture till here. Now I will take a pause for like 2 minutes. Just give me 2 minutes because I need to switch my screen. So we will resume in next 2 minutes. Okay, so now let's start with a few MCQ questions. Let's try solving them with whatever we have studied till now. We have completed kind of a lot. So let's try solving these questions. Okay, so first I will be giving you around 40 seconds to solve these questions, and after that we will see the detailed solution of the specific questions, right? So this is the first question. I will give you a 40-minute timer, and then we will see what the solution is. So the first question is, which digital gate performs the multiplication operation and NOR, or NAND? Try solving this question, then I will give you a detailed explanation of the question. It's a very simple question that we have already covered with. Yes, so we are done with the timer, and the answer to this, one second, and the answer to this question is option, the first option, that is nothing but AND gate, right? The AND gate works as a multiplication operation, right? So this is the first question. Now let's move on to the next question. Again, I will give you a simple timer of 40 seconds. Okay. Now, the question is, a three input NOR gate gives the output dash, and there are the different options that we have. I guess the question is visible. Oh, yes, it is visible, right? Okay. So, this is the question. Now, this is our timer. Try solving the question. Yes, we are done with the 40-second timer. And the answer to this is option 3, that is all inputs are low. Right? We are talking about a NOR gate. So whenever such questions are asked, the simple thing is to do is to draw the truth table, because from the truth table it is very easy for us to determine the output, right? So this is the truth table that we've drawn. In here we've considered the three inputs R, Q and P, and this is the output that we get when we perform the NOR operation, right? Okay. Okay, now let's move on to the next type of question. Okay, now this is a simple one. Okay, we are starting off with very simple questions right now, because this is our first time solving the questions. This is also very simple, not complicated. Let me just display the timer and give you the question. So this is our first question. What is the binary equivalent of the decimal number 5? It is very easy. I think 40 seconds are very more for this. You need to able to solve this in like 10 seconds. Okay, 40 seconds are done. How do you solve? We need to convert binary decimal number 5 to its binary equivalent with base 2, right? So simple, I'm giving you a technique, the 8-4-2-1 technique. So you need to identify the digits which sum up to 5. So 4 plus 1 sum up to 5. The 4 would be represented as 1 and 1 would be represented as 1 and remaining would be 0. So the binary equivalent of 5 is 0, 1, 0, 1. If we just need to say the question over here is asking only three outputs. So here you can see our answer is option A, 1, 0, 1. Okay. So since this is our very first class, we have solved very simple questions. But moving on, we would look at all the different questions from GATE as well as ESE, and we would have a quick brush up on all the concepts of digital electronics in this week. And we are tentatively planning to complete it till 6th to 7th of September of our digital electronics syllabus. And then we would also have a series of videos in which we are going to be solving the previous, specifically we will solve the previous year questions, right? Okay, so do subscribe to our channel for getting notified of all our live sessions, and the PDFs and all the notes that we are referring, and the previous year questions, practice questions, all the study material will be posted on our Telegram channel. So the Telegram channel name is ESE 2024 Buds Engineering Academy. The link is also in the description box. You can directly join. Otherwise, you can just search us on the Telegram application, and you can join the Telegram channel. Right. So that's it for today, and I will see you all in the next video. And we will try completing the digital electronics through our simplified notes. So thank you so much. Keep studying, and I'll see you in the next video. Thank you.